In this video, we will see what is the effective capacitance whenever capacitors are connected in series and in parallel. Okay, now when capacitors are connected in series, let's say 3 capacitors are connected. So I am giving a positive charge to this side. So what will happen? Negative charges will be induced on this side of the plate and positive charge will be induced on the other side of the plate. And what will happen to this positive charge? These negative charges will be bound by positive charge. This cannot move, but this positive charge will be repelled by this side and that will go to the other side, positive charge. So similarly, negative will induce here, positive will induce here, but that will go to the other side, positive and negative. So one thing is very clear, whatever the charge we are giving, that will be induced here. So plus Q minus Q, it will be the same amount here, plus Q, and it will be minus Q here, plus Q here, minus Q here. So one thing is very sure, that is charge stored in each capacitor is the same when they are connected in series. But the potential will be different. How? Because we know the equation Q is equal to CB, so V is equal to Q by C. Now, when these are different capacitors with different capacitance of C1 and C2 and C3, we know that V1 is equal to Q by C1, V2 is equal to Q by C2 and V3 is equal to Q by C3, V1 and V2. Now, what do we mean by potential difference? Potential difference is nothing but level difference. Let's say the potential difference in between these 2 points is 5, which means the level difference is 5. Now, in between these 2 points, if it is 15, so 5 down, then in the next level difference is 15, then here if the level difference is 10, what is the total level difference in between these 2 points? 5 plus 15 plus 10. How much it is? 20, 30, right? So similarly, if you know the potential difference V1, V2 and V3 separately, we can easily find the total potential difference that is in between these 2 points. That is nothing but the potential provided by the battery. So let's say the battery is having a potential of V, which is now given in between these 2 points. Now the potential difference in between these 2 points is nothing but sum of the potential difference in between these 2 points, then these 2 points, then these 2 points. So I could say that this V of the battery is equal to V1 plus V2 plus V3. Now let's say I am going to consider this arrangement as an equivalent system having only one capacitor. So this is C equivalent. Now what is this one? C equivalent, that represents these 3 capacitors connected in series to the same battery. So we know that battery is the same, which means here the voltage, this voltage is equal to the same voltage here. What is that? V1 plus V2 plus V3. Now here the voltage is V, which is V1 plus V2 plus V3. Now this is C equivalent, right? Now C equivalent, one thing is also very sure, which is charge stored in each and every capacitor is the same. So in the equivalent capacitor also the charge stored will be the same. So that is Q. Now we can substitute the values in this equation. What is that? V in between this point is equal to V in between these 2 plus this. So what is V1? Q by C1. So in this equation, V is equal to Q by C1 plus Q by C2 plus Q by C3. Okay. Now what is V? It's the same value in the effective or equivalent circuit, right? What will be V here? So we know equation Q is equal to CV. So V is equal to Q by C. Now I can substitute the value of V from this thing because it's the same battery, right? Only the difference is here 3 capacitors connected in this way. I have compared, or I have connected this, or I have simulated this as an equivalent capacitor having delivering the same thing what these 3 capacitors are delivering together. Okay, now this V is nothing but this one, and that I can get as Q by what is this C? That is C equivalent. Now I can cancel out all Q. and I will get the value 1 by C equivalent is equal to 1 by C1 plus 1 by C2 plus 1 by C3. This is a very important relation. Clear? In the case of parallel, it is very easy, which means when I am connecting capacitors in parallel, I am connecting one terminal of all capacitor to same point and similarly other terminal into the same point. Now, whatever the potential difference in between these 2 points, that is applicable to this, that is applicable to this, and even this. Which means whenever I am connecting a battery, okay, whatever the potential in between these 2 points in capacitor, these 2 points in battery, that will be the same potential difference in between these two. Which means in between these two, what is the potential? V1. In between these two, what is the potential? V2. In between these two, what is the potential of third capacitor? V3. But as all these points are, all these three are same, connected to the same point, and other side, as all these three are connected to the same point on the other side, I could say that V1 is equal to V2 is equal to V3. The reason is, in your examination you have to say, because all of them are connected to the same point. All one terminals are connected to the same point and other terminals are connected to the other side of the battery, which is also a common point. Now, another important relation is, let's say a charge of Q comes here. It has got 3 different paths. So Q1 will go through this one, Q2 will go through this, Q3 will go through this. So I can say that whenever Q comes, that is been split into 3 different capacitors as Q1 plus Q2 plus Q3. Now equivalent circuit, one capacitor and a battery. What is the value of C equivalent from this? When we are comparing, we have already derived. What is the value of C equivalent? C equivalent is equal to Q divided by V in this circuit. Okay, anyway we are not going to use it here. At the end we are going to substitute this value. So C equivalent is equal to Q by V. Now anyway in this equation we will substitute the value. So what is Q? I can substitute what is Q here, that is C equivalent into V. So on the LHS I am going to substitute the values of equivalent circuit. Even here also on the LHS, Q divided by C equivalent. Similarly in the LHS Q, I am going to substitute the values from equivalent circuit. What is that? Q is equal to C equivalent into V. Now here what is Q1? We know Q is equal to CV. So it is C1 V1 plus Q2 is C2 V2 plus Q3 is C3 V3. Okay. Now all V1, V2 and V3 are same, right? So this will be C1 V plus C2 V plus C3 V. I can take V in common, C1 plus C2 plus C3. These V will cancel. C equivalent is equal to C1 plus C2 plus C3. This is another important relation. Sorry. Now whenever we are deriving equations for effective capacitance in series and parallel arrangement, you have to draw 2 pictures. One is the actual picture and other one is equivalent circuit. So here in this case, actual picture, equivalent circuit. And on RHS, do the values substitutions for the actual picture, and the equivalent picture you can do on the LHS. Similarly, actual picture I am substituting on the RHS. On the equivalent picture, all the values what I have derived, I am going to substitute on the LHS. You can change LHS and RHS, but one side it is actual picture, on other side it is the equivalent circuit. Clear? C equivalent is equal to this one, C equivalent is equal to this one. Another important takeaway from this is, let's say we are connecting one capacitor, 1 microfarad and 3 microfarad and 5 microfarad in series and parallel. When we are connecting in series, the effective capacitance will be lower than the lowest one. Which is the lowest one? 1 microfarad. So here the effective capacitance will be less than 1. In parallel, effective capacitance will be greater than the greatest one. Which is the greatest one here? 5 microfarad. So the value will be greater than 5. Just substitute the value here. What, as per the equation, C1 plus C2 plus C3. 1 plus 3 plus 5, which is 9. So 9 is greater than 5. Thank you.